Hi there, I'm playing with some random stuff again, and this time let's begin with an SSD drive. This is a Plaint LS150S. It's a 150 gigabyte SSD drive. And it is one of the first, or maybe the first, commercial grade or enterprise grade SSD drive. Plaint was a company that was founded in September 2009. And this disk has a manufacturing date of 14th December 2009. So this was one of their very first products. Plaint then was bought by SanDisk in 2011, so they only were around for 2 years, and well, it's pretty interesting what's inside, so let's have a look. So the first piece that fell out was this little plastic window. There is an LED. Yes, this SSD drive has an activity LED, and there is also a rubber cover here that covers this little connector here. We will see later what that is. And we have a ton of memory chips. So that's 1, 2, 3, 5. 4 by 4, that's 16, that's 32 on this side. And these boards are connected by large multi-pin connectors like that. So there is nothing else on this board, but there is another board with another 33 chips. And with this strange interface here, 2 metal spacers. I guess that's for heat conducting, at least a little bit. So we have another board here, nothing on this side. In fact, it's the same board as this board, but here they left the connectors away because that's the top board. Maybe there was a version that was a little bit higher with more boards, I don't know. Then we have 2 more spacers, and we have another board with 16 chips here and something that looks like a CPU with a lot of thermal grease, which is more like silicon based, not the usual white stuff that spoils everything. Another 16, so we have a total of 96 Samsung flash chips. And here's the CPU board again. I cleaned up all this thermal paste. It seems that here we have some power chips from Linear. I don't know, I haven't looked them up, but they look like power supply, power converter chips, something like that. There are also big resistors and capacitors on this side. Then we have something that looks like DRAM, which makes sense because we have an entire computer here. And we have the large chip that says Plaint HEMI V12. Okay, that's an engine, obviously, from a car. No, I think it's something ARM-based, maybe. We can have a look at this a little bit later. So yeah, that's the controller board. Let's talk about this strange connector here. It looks like a micro USB, and well, it is a micro USB connector, but it's not a micro USB connector, it's a serial connector. They just used the same form factor for that. So I built a little cable. I took a micro USB cable and converted it into a serial cable. Here is the pinout, just in case you're interested. Black is ground, goes to pin 5. Green and white are the data lines, go to pin 2 and 3. And everything we need now is a terminal device, and I take my iPad with an RS232 adapter. I found this serial cable here for iPads or iPhones from Red Park, and this is not a sponsored video. I bought this because I wanted one, and this plugs into my iPad, and with the console app we are ready to see what's going on. So let me first connect everything. That goes here. And we need some power for the drive. That comes from here. Okay, let's see what the drive tells us. Okay, that's it already. I must say this drive here has a problem. It stops after 4.6 seconds and it prints out a lot of error messages because I tried something. I had multiple of this drive model, and I thought, well, why not take one board from another drive and stack it between these boards, because it's the same board. You can stack them on and on and on and on, and maybe that gives you a bigger drive, but it turns out it messes up all the CPU, the auto configuration and what happens. And well, I took everything back, and now it has a problem because it recognized an additional board. It made a file system check. You could see the percentage counting up, and now of course there is one board less, and now it's completely confused. The problem is, on the serial port, I don't know what I can send. There is no command that is recognized. So whatever I type on the iPad, it doesn't react. So I'm pretty sure there is a way to reconfigure the whole thing, but I haven't figured that out. Okay, we don't need the keyboard here. So the last line here says UART output disabled after 4.6 seconds. On a working drive, it's about 16 seconds until it has well, done everything it needs to do. It starts with, of course, UART initialized, DRAM initialized. What I said, it's DRAM inside. We have a date code. It says September 2009. There is a internet address for, I don't know, firmware maybe, including an exact folder. Maybe that's an internal folder of the drive, or it's something on the internet that the drive could download at the time. It's a model LS150S, and there is the serial number. Yeah, I just scroll it through. You can read that if you want. So here the problems are starting. Rebuild, degraded. That's always a bad thing to read. There is more library. That's the same firmware info again. Where? Oh, here, file system in errors. Expected 29, got 33. Something is wrong. Yeah. Okay, that's about the SSD drive. All right, next item. We have this weird looking tool. It has a hex drive here on one end, an extra long one, and it has a Torx bit, a security Torx with a hole in the middle, and it has a handle. Yeah, what could that be? Or what could it be used for? Well, that's the Itanium tool, and it makes only sense if you have an Itanium CPU board. And that's exactly what I have here. That's a CPU board from an HP RX6600. That's a huge machine, about, well, 8 rack units high, and it has space for 4 Itanium CPUs, Intel Itanium, for those who don't know what I'm talking of. And the earlier Itanium boards or processors had large heatsinks where you needed this extra long hex bit, and this is to reach the socket lock lever or lock, yeah, the pin lock thing. You turn it around and you see how the CPU moves. And the Torx bit was used because the DC converter here was normally screwed down to the board. Here they had another mechanism. It has a big clamp on top, so we don't need that one. And then the CPU comes out. So that's the CPU chip, that's the DC converter here, and it's connected with this thick power cable here. So, and in fact that makes sense because on modern CPUs about half of the pins are only for power supply, power rail and ground. Normally it's divided diagonally, so you have all the power pins here and all the data pins on the other side. And here they made a different approach. They attached the voltage regulator, the power supply, directly to the chip. The chip extends to here, where it is screwed down to this regulator board. And all the pins here are only for data communication, so you don't need all the pins for power. Hundreds or thousands of pins for power. You can save some pins. Pretty clever. On the board itself there is not much on it. We have some power regulators here. Big power connector goes to the CPUs. We have a clock generator chip here, which is pretty interesting. It takes a 16 megahertz clock according to the data sheet. Here we have a how much? Yes, 16.66 megahertz clock. So they did it exactly as it was written on the data sheet. This chip can be programmed to output any frequency from, I think, 1 megahertz to 500 megahertz. So it can scale this 16 megahertz up or down, whatever you want. There is a test connector, and you can see from the shape it's meant to for a coaxial connector, like this tiny little golden screw connectors here. It has 4 pins around ground, and it has 1 pin in the center for the signal. We have a similar yes, we have a similar connector here, and you can see the center pin is going somewhere. It's of course an HP board, and it says product of Germany. I think that the board itself has been made in Germany, because the sticker on the other side here says product of Puerto Rico. And I think that's where they put the components on it. Well, yes, it's an international company working all over the world. Then what else do we have? We have a couple of chips here. That's everything. Just a bunch of transistors down here. That's the power controller. It checks all the voltages and tells the system if everything is okay. I think it will also measure the voltages. Then we have a I2C I/O chip that has a couple of analog digital I/O ports used for whatever they need. Then we have an additional I2C I/O chip. This has also some memory inside, some ROM. Yes, I think so. This is only I/O, and here we have an I2C switch chip. So because we have so many I2C chips, they may need a switcher here. I guess it works like an Ethernet switch, but well, for I2C, so you have one input, many outputs, can hook up all your necessary chips together, something like that. I don't know, maybe you can see the part numbers, maybe. I think you can. Okay. Oh, and something important I almost forgot. We have 2 huge connectors here. That's where the memory modules are to plug in. Memory modules, you can imagine a box about like that, a big plastic box with the actual memory modules inside. We have 2 of them. That's memory extender 0, that's memory extender 1. Memory extender 0 is for the CPUs here on the top. Memory extender 1 is for the CPUs underneath. And I think the maximum number of CPU modules is about, well, maybe 60 modules. I'm just making that up, but yeah, it's around that number. Then there is another interesting part that belongs to this machine. So that's the backplane board. Here is where this CPU board connects to. It goes like that. So the CPU board is mounted in a big drawer. So you slide it out of the machine, and this backplane board stays inside the machine. And you may have noticed it is extremely thick. It's, how much is that? Let me see. That's 6 point something millimeters. Is it 6.3? Maybe, yes, that's a 1/4 inch. Is that right? Yes, I think so. Here on the back side is a connector for the I/O board. That's where all the PCI cards and all that stuff goes in. That's on the back end of the machine. Also the I/O board can be moved like a drawer. And here are 2 large connectors for the power supplies, 2 power supplies. And I think that connector was for the fans. I'm not sure, there was a cable with a connector. I think that's fan power, probably. So that's almost the entire machine. Interesting here is, this says, oops, let me zoom in. Product of Korea. It's a little bit difficult with the focus here. And it has the LG logo on it. It seems they also made PCBs for other companies like HP. And I'm pretty sure you want to see that CPU again a little bit closer. Let's remove that voltage regulator here. Maybe we can also remove the heatsink. Okay, there is this back plate that comes off. Okay, more screws. It is pretty heavy because the heatsink here is made of copper. Best material for that, but also quite expensive. But this machine is from the days when the price didn't play a big role, so it wasn't that important how much that cost, because people were willing to pay. Okay, I think that's the way to remove the CPU from the heatsink. Boink. Okay, yes, that's it. Well, you see, that's the CPU. That's all the power connectors that are normally on this side, but here they decided to put them on an extra space and leave the socket for the data only. Oops. So what is it? It's a 1.6 it's a 1.6 gigahertz. Is that it? Yeah, I think 18 megabyte cache. I need a magnifier glass. Does that work through the camera? Well, doesn't make much of a difference. It makes a difference for me. 18 meg, 533 megahertz. Well, that's the front side bus. 400, maybe another front side bus, memory bus. Made in Costa Rica again. Okay. Okay, it just says Intel Itanium, copyright 2006. And here is a close-up view of this DC converter. Has a large heatsink, a lot of transistors underneath. It has one input voltage here. I think it's probably 12 volts, but I'm not sure. And all the voltage converters, and then this. That's the style of connector we use today for the CPU itself. It's this spring contact socket here that you find on the modern Xeon processors, or well, on almost all processors. and they're pretty easy to damage, as you probably know. Yeah, so they already existed in 2006 and we have them everywhere today. And for the last bit of the video I have some small parts. So first of all, were these heat sinks. They're pretty funny. They are also from this RX6600 server. And the interesting part is, first of all, they are round. They have a screw here. They have this plastic clip that clips over the memory controller chips. And the heatsink then is screwed in until the pressure is good enough to cool the chip. Here you can see the marking of the chip itself. It was one of the ceramic chips with the silicon chip that is visible here with no housing around, so you're cooling the silicon chip directly. Yeah, I thought that's funny to see. Then take this one first. We saw a big SSD and now this is a very small SSD. These were mainly used in embedded systems like point of sale systems where you don't need a large operating system. So this one has 32 gigabytes and it plugs directly into a SATA port on the main board, and that's why it is called a DOM, a disk on motherboard or main board, and of course SATA. And now you may ask, how does that work? Because every SSD needs power to work. Well, first of all, there is a small connector here. You need a special cable with a tiny connector and you supply 5 volt to that. Or on the other hand, you have a main board that has pin 7 power. Pin 7 power works pretty simple. This is the layout of a normal SATA connector. You have 3 ground pins, pin 1, pin 4 and pin 7. The 2 last and the center one, you have the data pins A and B, plus and minus for each. And they simply took pin 7, disconnected it from ground and connected it through a short circuit detection circuit to 5 volt. So if you have a main board with pin 7 power, pin 7 is no longer ground, it's now plus 5 volt. And if you plug that in, it takes the 5 volt from that pin 7. The problem is if you plug any other device in or just a SATA cable, in a cable all the grounds are connected together. Of course, they want to save some wires, and this would short out the 5 volts. So we have a short circuit detection here, and if that detects a cable or another device that doesn't support this pin 7 power, it disconnects the 5 volts and probably connects it to ground or leaves it open. I don't know how that works. And yeah, so you can use that connector for any type of SATA drive. But you can also connect it to a SATA DOM and you don't need this extra power cable because you have the power on pin 7. And last but not least, we have this little item here. This is an electronic price tag found in larger stores nowadays. They replace the usual paper price tags on the shelves. It has 2 buttons here. If you press them simultaneously for a second or a little bit longer, maybe a little bit longer. Yep, it will reset the display and maybe reset itself. And as you can see from this strange flickering here, it's an e-paper display. Let's do it again. And it also can display not only black and white, but also red. You can see that in a short time. Well, it should turn back to this barcode. Let's try it again. Yeah, now it does it. And if you look here, you can see it turns from black to red. It needs a couple of refreshes to change the color, but now we have a two-color display here. Okay, let's take it apart. That's what you always wanted. First of all, we have batteries. That's the main part of this whole thing. Two batteries. CR2450, that means 24 millimeters diameter and 5 millimeter thick. That's what this number means on coin cells. And we have, of course, two of them. Then we can remove this front glass here. By the way, this is glued in, and this has a rubber gasket, so the whole thing is waterproof. This is because some of these items are placed inside fridges, and if they get hot and cold, so maybe moisture will accumulate inside, and to prevent that, they are made waterproof. Okay, now the PCB should pop out. Let me push that a little bit. Yep. Okay, there's not much to see. So we have the e-paper display. There is a little LED. I think that's only on when you're programming it, so it will tell you some status or data communication. It has a connector, so the e-paper display can be disconnected. You can probably use that for a project with your Arduino or Raspberry Pi. I don't know if there is an interface board for that. Then we have a chip, a little crystal here, oscillator. That's the LED from the other side. It looks like it's at least a two-color LED. Maybe that's the two buttons here. And we have here the Wi-Fi connection that goes to the case, to these two spring connectors here, and then you can see that's the antenna down here. And yes, that's the whole antenna here. So that's the Wi-Fi antenna that connects to the PCB, and that's where data, well, how it is programmed. This is the serial number of this display here. It's a barcode. You can read it with a barcode reader to get this number into your system, and then you can send data to this display here. like all the other displays in the room. Okay, that's about that. Tiny little thing. Nice to look at. By the way, the small ones here are about $5. If you buy them in 10,000 in a 10,000 pack, they are probably cheaper, but that's about what it's worth. Okay, thanks for watching.